Okay, this is number 21. A rocket's going to low Earth orbit. 95% of its launch weight is fuel. Now that 95% is MF by definition. So MF is 0.95. So if MF is 0.95, then minus minus M1 over M0 must be 0.05. 0.05. So 1 minus 0.05 is 0.95. So 0.05 must equal the e to the minus delta V over VE, which is 1 over the mass ratio. So if that's 0.05, then 1 over that would be e to the delta V over VE. 1 over 0.05 is 20. So if I come into my chart at 20, hit the blue curve, I see the ratio of delta V to exhaust velocity is 3. So if that ratio is 3 and I'm given delta V at 32,253 meters per second, I divide that by 3 and that'll give me 10,751 meters per second for the exhaust velocity, and that is the answer. Okay, this is number 22, and number 22 says an asteroid was spotted by the Juno satellite. The astronaut was spotted at 5.531 AUs from the Sun at its apogee. So it's orbiting the Sun, and the AUs is 5.531. So using Kepler's third law, what is the period of the asteroid around the Sun in Earth years, accurate to 2 decimal places? Well, we'll see. The formula to be used is that the AUs cubed, so 5.531 cubed is 169.2, is the period in Earth years squared. So if that's that is 13.01 squared, so 13.01 must be the Earth years, and that is the answer. Period squared equals the AUs cubed when you use Earth years and astronomical units. And the example we used in class was for Mars. If Mars was 1.524 AUs, if you cube that and take the square root, you get 1.88 Earth years. So that is how you do this problem. Okay, this is number 23, and you are chasing the ISS in the green circular orbit, this green orbit, and your orbital velocity is the same as the ISS, and that velocity is given 7977 meters per second. What is the period of the green orbit in seconds? Okay, so we know the velocity, and if we know the velocity, then we actually know the radius from the formula v squared equals gm over r. Except this time we're going to solve for the radius. So that turns out to be gm over v squared, which is 4e14 in the metric system, divided by 7977 meters per second squared, and that will give you 6,286,093 meters. Now once you have r, you can find your period of a circular orbit, the circumference divided by the velocity. The circumference divided by the velocity will give you the period. And so the circumference is 2 pi r, where r is 6,286,093. The velocity is 7977, and if you divide the circumference by the velocity, you'll get a period of 4,951 seconds, or 82.52 minutes. That's it. Okay, this is number 24, and we have the green orbit, which was given. We know the height above the Earth, what we call RT. That's the yellow one here, and we know the radius of the Earth. That's also given to us here. That's given. So if we add RT plus RE, that gives us the height, the R for the green orbit. And that is going to be equal to the sum of RT, or 25,404,199. Now, once we know that R, we can compute the velocity in the green orbit, which is not given to us. So the velocity, we know from our basic equation, v squared equals gm over r. We know r, we know gm is 4e14, so we can compute the velocity as a square root of gm over r, or 3968 meters per second. That's the velocity in the green orbit. Once we know our velocity, and we know the distance between us and the satellite, that's given to us here, 222.5312. Then we can find the time then to the space vehicle from our present position is equal to the distance divided by the velocity. So that turns out to be equal to the distance given here, 222.5312, divided by the velocity we just figured out, and that's 560.8 seconds. And of course, that difference between us and the satellite is going to be the difference in the periods. That's how we work this problem out, the difference in the periods. But that's all the problem asks for, so we're done with this one. Okay, this is number 25, looking at 1G level flight that stalls at 95 knots. If the maximum number of G's is 6.1, what's the maneuvering speed? Well, the formula for the maneuvering speed is here. CL max would be equal to 6.1 in here, and then I would have maneuvering velocity in here. But I know the stall velocity. So this equation, if I wanted to convert it to the stall equation, I'd have to divide by NZ max. Divide both the numerator and the denominator by NZ max, because I have to keep CL max the same whether I'm at stall or whether I'm at maneuvering speed. So if I divide the numerator and the denominator by NZ max, I'll get 1. And if I put NZ max in the denominator, then it can only enter the airspeed. So the airspeed for 1G would be the stall speed. If I put inside the square root sign, it would be the square root of 6.1. So the square root of 6.1 times 95 should be the answer. The square root of 6.1 is 2.47. You multiply that by 95 and you get 234 knots. And so the answer is 234.6 knots. And that's it. The last question on the exam is an extra credit one for 2 points. This shows you the Colesman window right here, where you set 2992 for a standard atmosphere, but you'll set your local altimeter setting depending on the atmosphere that you're actually flying in. And the question asks you, it says you're planning a flight from SLO, which is 212 feet MSL, to Santa Barbara, which is 0 feet. The altimeter at SLO is 2959. The altimeter at Santa Barbara is 2859. But you forget to set it. So you will have the wrong altimeter setting at Santa Barbara. And this is a high to low. You're flying to low pressure. So high to low, so the altimeter will read too high and give you a false sense of confidence. Every inch of mercury is 1,000 feet. You have 1 inch there, so you will read 1,000 feet high for this particular problem. If these altimeters change, just take the difference between them in inches, multiply by 1,000, and that would be the correct answer. This goes back to the setting where you're flying from high to low, and here the difference in this particular case is what do we got? We got 2992 over here, and the altimeter should be set at 2836. So the difference between 2992 and 2836 in inches times 1,000 feet is 1,560 feet difference. So your altimeter will read 1,560 feet high, give you a false sense of security, and you could fly into anything that's of high altitude. That's it.